Good morning, everybody. I'm Luca Ruggero, EMEA Sales Director of DP Technology, and I'm here today to introduce our guest partner, Kennametal, that will show us and will give us some details about their product for the solid and carbide end mills. And on the other side, we have ESPRIT that will show you the profit milling cycle that will allow you to program this tool in a correct way. So from Kennametal today, we have Gianfranco Cardi. Gianfranco, welcome.
Thanks, Luca.
That's great. And on the other side, we have Andrea Poggi, that is the technical manager of Italy, that will introduce us the auto program ESPRIT in a correct way with the profit milling. So Gianfranco, first of all, we have our partner that is Kennametal. We're working together since a few years. And if you can introduce yourself and maybe the company Kennametal for the few people that don't know the company.
Okay, absolutely. And thank you very much for the introduction, Luca. So we are going to have a presentation on dynamic milling or high velocity milling with new tools from Kennametal. But before to start, so welcoming Kennametal. My name is Gianfranco Accardi. I'm a manager of Regular Plus Specialist at EMEA level. I'm an Italian located in Milano. I'm with Kennametal since 14 years and a half, roughly. So, and I had always covered function supporting products, starting with turning, then back to my main skill that was milling for a period of time. And then for the last 8 years and a half, I'm leading the product specialist team at EMEA, as said before. But of course, it's important also for me to introduce the Kennametal organization. So this is a snapshot to show Kennametal worldwide. As you may know, Kennametal is one of the main cutting tool supplier. So it's an American company located in Pittsburgh, Pennsylvania. Founded in 1938, as per today, we do have more than 10,000 employees, serving 8,000 customers in 60 different countries. So we have a lot of patent active, as you can see, and of course we are able to serve customers everywhere with the latest technology. So of course we are not here to talk about Kennametal only. But I would like to invite you to learn more about Kennametal following Kennametal website, our application, and our YouTube channel, where you can find more information, of course. But for the sake of time, I would like to go straight to the subject today. So we are going to talk about solid carbide end mills, and specifically roughing, which is the most challenging application. Okay, so also finishing sometimes have some trick or issues, whatever, but the roughing is really where we have the highest timing cut. Okay, so where we need to face some challenges. So I like to call challenging instead of issue or problems, because the challenge we can overtake and will be important. So let's see, talking about conventional milling, roughing. So I would say the first challenge we have to overtake is the breakage of the tool, especially when we are working after minutes or hours of work. So the cutting forces and the wear is going to increase, and unfortunately it's also common to see a breakage with conventional milling. Another important topic is the deflection of the tool. So we need to think about that the hand mill is vinculated by a chuck at the end. So let me put my laser pointer so to explain what I'm talking about. So we have a chuck here that vinculated the hand mill. Longer is the overhang of the tool and higher is the deflection according to the cutting forces on the conventional milling. Another important topic to be evaluated also is the edge stability. So when we are doing roughing, especially in full slot, the edge of on the hand mill is the first suffering due to breakage or damaging the edge of the corner. And of course, this will have an impact on the tool life in general. Then also chip evacuation is something that, especially when we are doing pocketing or internal application, so not managed properly, the chip evacuation could be an issue for the recut standpoint, And if we recut the chip, we can go to the first challenging, which was the breakage. Okay, so of course we may have other challenges, but I consider this the main four, and we can summarize all these challenges in one single sentence to have a process reliability, which is very important when you use critical biodynamics.
Yeah, absolutely. Gianmarco, I like the concept of challenges because we want to find solutions to these challenges. And I know that Kennametal is looking at these challenges since a while. So could you tell us something about the solution that you are proposing?
Absolutely. So Luca, thanks for asking or introducing the next slide. So we need to keep the focus on the reliability, because reliability can drive productivity and reduce the complexity also. So what we need to do from my point of view, we need to change approach. We need to change machining strategy. So still on the left, you can see a scheme for the conventional milling, where it's clear that we have a large radial engagement and limited axial depth of cut. When I say change approach, that means for me that we need to go changing the way we want to machine the workpiece. And this is the perfectly introduction of the dynamic on high velocity milling, where we basically change the idea, increasing the axial depth of cut, reducing the radial engagement. In doing this, as you can see here on the features or the benefit from the dynamic milling, we can definitely, and also easy to understand, we can reduce the cutting forces, we can reduce the pressure. We are for sure going to reduce the radial engagement as said, but we are going to use the cutting length, the entire cutting length of the tool, that in case of the specific tool for dynamic milling, we can push up to 5 times D in depth of axial depth of cut. We are going to reduce the vibration. We are going to, preserve the corner stability as well. We are going to reduce the temperature during the application. And all these benefits that you can see are listed as a plus against the conventional milling, where the only plus is the biggest radial engagement. At the end, it permits us to increase the feed and speed, so to boost our cutting condition during the application. That means increase the productivity and metal removal rate, as well as the process stability. Another important point, when we are going in more in-depth axial depth of cut, we are going to have more axial contact point, as you can see here. So the cutting edges are more in contact with the workpiece, and this is going to limit it also the deflection of the tool itself. So we can really list it a lot of advantages, but I would like to highlight the cutting condition, the productivity, and last but not least, of course, the stability and the reliability of the process.
Yeah, so there is really no battle. So the conventional
it looks like so.
Yeah, dynamic is really impressive, all the plus that you can have. But I saw that you have a really underlined feed and speed. So how you can increase so high the feed and speed? Okay,
so yes, to explain this, I created the next slide a little bit. So where we go to the basic of milling. Okay, so it's not going to be a technical training today, but I think that is important for us to understand the concept behind the relation between the radial engagement that is named LE, the cutting speed VC, and the feed VF. Okay, there is a relation that link all together. So and it's also quite clear to understand. So you need to think about the radial engagement, define the timing cut. So if you can now see this image, this picture, it's quite clear to understand that when I increase the radial engagement, okay, so of course the cutting edges is going in touch with the material for the certain time till exit of the material. So larger is the radial engagement and higher is the timing cut. When I have a higher timing cut, of course, I'm going to increase the friction between the solid carbide end mill and the material. The friction will generate the heat, and the heat is going to generate lower to life. Okay, there is really a strict correlation with the temperature generated and the radial engagement. So using a small radial engagement, I can definitely increase the cutting speed drastically, I would say, because the temperature generated is going to be lower. So I can boost the cutting speed. And of course, the cutting speed, when it's high, we know that for the calculation, cutting condition calculation, cutting speed is extremely important. Increasing the cutting speed will land with a higher feed at the end of the day. So we need to consider also another important topic. So when the cutter is moving, it's always the center is that moves. So if we move 0.1 millimeter with the center, having a small radial engagement, the cutting edge is not moving 0.1. So, but we need to keep constant the average chip thickness. So that means in order to keep constant this value, we need to boost the feed per tooth as well, in order to have the cutter work properly, okay? So it's not just the heat generation, it's also the average chip thickness concept should be considered. So we have two advantages, and this is very important to remember. The smaller is the radial engagement, higher is the feed per tooth, and this is a simplified formula to calculate this, but what we are doing also in our catalog, we are giving a compensated value for the FZ, feed per tooth, in order to keep constant the average chip thickness. Two very basic concepts, but I would say key for success of the application.
Okay, now it's definitely more clear. And the concept is really that you can move faster and you can have a longer term to life because the heat it will be much less. But
yes,
you can
absolutely.
apply
We
this
have
technique.
example. Sorry, Luca, go
Okay.
ahead.
No, I just want to underline after the formula that the basic concept behind is that you can cut faster and also you have a longer to life, and it was perfect. But you can apply these things on every kind of material.
Absolutely. So we need to think that this kind of strategy, born many years ago on diamond segment, where the customer were facing the issue to machine hard steel with a high Rockwell C, and was simply impossible to go full slot. So they developed this kind of application. It definitely is possible to go on each material. But this link to me to now going a little bit about our Kennametal solution, specifically for dynamic milling. So I like this, let me say, slide to explain what core means for Kennametal. So core is a king of roughing. So, and I'm going to introduce what we do have today, depending on the material we want to focus on. Definitely, maybe you saw on the social, because we launched last calendar year already. So we have the Core 5 for the dynamic milling aluminum. So it was the first cutter 5 fluids for high velocity on aluminum. Then we launched as well the TCDE. That was the first, let me say, dynamic solid carbide end mill launched by Kennametal, and this was our weapon to go on steel, stainless steel, cast iron, so in general on all the materials. So with these two products, basically we can cover all the material that we can find on the market. But last but not least, I would let me say as a highlight to give you a pre-information that a new and outstanding cutter is going to come. So, and at least it's coming soon. A little bit hide the picture because we have not yet launched, but something new is going to come very soon. That will help the material coverage.
Okay, it's still top secret, or we can have some data about this tool, the release of this tool.
Well, what I can say, and probably I cannot say too much, but in general, so if you link the color of the text to the material according to the ISO, you can simply also understand that it's going to be a new solid carbide end mill focusing on difficult to cut material. Okay, so and very unique features. I cannot say more, but let's think about when titanium or nickel-based alloy will be in the arena. So we may have something new. Okay.
This will be the tool. Okay, got it. Thank you.
Okay, you're welcome. Okay, guys. So and then what I wanted to do very quickly, I would like to provide a couple of highlights on the already launched platform, the Core 5 and TCDE. So maybe you have seen already. I said the Core 5 is a kind of unique cutter for aluminum. So we have an optimized helix angle 35 degree for this kind of material. So the length of cut in general is 3 times D, but with a simple custom solution, we can go easily to up to 5 times D, but standard is 3 times D. So we have in 5 fluids and equal spaced. The internal coolant capability, especially, is a feature very important when we are going to do pocketing. Also, the core of the cutter, and this is something very similar when we are going to talk about dynamic solid carbide end mill. So because we have the core generally is stronger or is larger compared to the standard solid carbide end mill, because we want to engage more the axial depth of cut. So that means we may have deflection, and adding a specific or proprietary core design will help us to reduce the deflection. Then, of course, we have extremely important as well, always something to manage the chip evacuation, okay? On the Core 5, we have the chip breakers specifically designed to machine non-ferrous material. On the TCDE, we have a chip splitter, same logic, but slightly different design. On the sharp edge, we have a sharp edge and the corner radii versions. And the sharp edge, you have also the Viper facet included, because sometimes it's also important after the roughing to make a kind of finishing application, and you can make as well using the Core 5. It's not just the roughing tool, which is the main feature of this, but if you want, you can also achieve a decent or good surface finishing. As you can see here, we don't have a center cutting that is not related to the internal coolant, so it's the design of the 5 fluids of Kennametal not having the center cutting, but it's not a limitation for the ramping. We can go ramping, of course, up to 4 degrees, without a doubt, and if you consider the highest cutting speed, it's not a big deal, so the 4 degrees, so it's more than enough. Going to the TCDE cutter, is basically starting from the same logic, 5 fluids, unequal fluid. So here we have changed the helix angle from 35 to 40 degrees because, of course, we have higher cutting forces on steel or cast iron, whatever. So that means that the higher is the helix angle and lower is the deflection, because the helix angle helps you to reduce the radial forces and to increase the axial forces. So the left radial forces will lend to less deflection. We have 3 times and 5 times D length of cut. As said before, the core is unique and designed to machine with lower radial engagement. So the suggestion have maximum 10% if you want really to go to the dynamic or high velocity milling. The cutting edge is stronger. We have a tail end of cutting edge that allow us to push the feed per tooth. And then you have a specific chip former. So think about to engage this tool 5 times D. We are going to create a stress point in the material, and we are going to better manage the chip evacuation, producing 5 different chips instead of very long chip following the helix. Okay. So also here, we don't have the center cut, but we have anyway the capability to go ramping up to 4 degrees. Everything is good on the slide, without a doubt, but what we wanted to do for this webinar today, also demonstrate what we are talking about in collaboration with ESPRIT. We created a demo that I named the slide from the slide to the real chips with the TCDE. So we are going to machine a P3 material steel 4140 with a 4 fluids solid carbide end mill, steel Kennametal. So maybe you know the name RV1, diameter 12, and with conventional milling, and make the same application using the ProfitMIliing of ESPRIT software with the TCDE, the last cutter we saw before, okay, diameter 12. As you can see, we try to maximize according to the diameter, the length of cut. So it will be not possible to do one single pass with the conventional milling. So we are going to see how it works. Okay. So let me put this video without sound because you anyway will not be able to see. Okay, these two videos will start simultaneously, and then we can debate about the cutting condition. So on top, you can see the conventional milling. And for the conventional milling, of course, we didn't want to use very conservative cutting condition, okay? So we are going to use really realistic parameters, cutting speed 140, depth of cut, considering 12 millimeter, the cutter is 1.5 millimeter axial depth of cut with a 40% rolling engagement. It's pretty challenging application, okay? Or 4 flutes, 0.08 millimeter per tooth. So the feed is around 1,200 millimeter per minute, so which is pretty decent application, okay, in terms of cutting speed and feed. So if you see here where the TCD is right now, is already above the type of application. So, and because we can do what I was explaining before, so 300 meters cutting speed, full depth of cut, 10% radial engagement, of course, adding one teeth more, 5 versus 4, we can push even more. The feed per tooth is 0.1, is still also conservative, we can push more. So we basically pass from 1.2 to 3.9, almost 4,000 millimeter per minute, and having a great advantage for the material removal rate standpoint. So you can see here, and unfortunately, on the conventional, we also had divided the radial engagement in doing this kind of application here, because was 40% radial engagement on this application specifically was too high. So we decreased to 20% to be on the safe side. So basically, we are almost at the end. And then my partner, Andrea, will explain exactly how we made the program here to, let me say, to really boost the dynamic milling. Now the last application is doing the helical interpolation. So it's important also to mention the dimension of the chip. On the external, you don't have any issue. But if you do pocketing with a large chip, it could be a problem for the chip evacuation. When we are dynamic, we are producing very small, okay, chip. So in total, the dynamic milling application was 2 minutes and 14 seconds done. So here, of course, I'm not going till the end because it's quite long, but we know already that the time to make the same part will be 5 minutes and 53 seconds. So as the takeaway, more than double metal removal rate compared to the conventional milling, and less than half cycle time, okay? So there is really a lot of advantages. And of course, here we are not measuring the tool life, but I am quite sure the tool life is going to be much longer also with the dynamic milling. So not just this tool, but also plus the tool life. So this was basically my last slide. So I thank you all for attention, and I hand over to Luca.
Thank you, Gianfranco. Was quite impressive. So you saved more than 50% of the time, and we didn't measure really the tool life. Okay, I just want to remind to all the attendees that if they have some question, they can use the chat of the question area of the GoToMeeting. So I will pass the ball in the field of ESPRIT, and Andrea Poggi will show us how to program the same part and how to use the ProfitMIliing.
Good morning to everybody. I'm Andrea Poggi, and I'm a technical manager for DP Technology Italy. Now we'll see how to program this part very easily with ESPRIT. First of all, the first operation is a circular contouring operation that you saw in the video. I make geometry for this, for example, from the center. I have make this, okay. Okay, this is the circular feature for to make my operation chain, and I program this contouring operation from the scratch. And I program with traditional milling. I set default to all my parameter, and I make circular contouring. Okay, I choose my tool. It's for cutting edge tool, handmill. Of course, you can see the preview of the tool and the tool holder also. And you can see the shape of the tool and also for the holder. Okay, cutting parameter like this, 0.08. Okay, and I want to use the stock automation for calculation. The strategy, I have to manage the step over. I take 40% is 4.8 of step over, and I want to have 35 of depth with 1.5 times of the diameter of step, incremental depth. Okay, and calculate. Okay, I have already mounted my fixture and workpiece on the machine. I have used a DMG Mori DMU 75 monoblock. You can see the machine. For ESPRIT, the simulation is very important because we have exactly the real machine. We have a digital twin of the real machine. It's very important to avoid collision and to avoid eventually out of stroke in the operation. Okay, let's start with simulation, like the video you saw, the tool, and start. In the right of my screen, you can see the axis, like the control of the machine, and also the elapsed time for to have an idea of the cycle time, and the value of the axis. You can see also the feed motion, the feed rate. There is a difference between this programmed and the video you have seen. I change the priority of my work. Is not width but depth. Okay, directly on simulation, and I have the contouring operation equal to the video. Okay, accelerate a little bit and so on. Okay, just 1 minute for this operation. Now I want to remachine the lateral side of the workpiece. I choose the all the solid model, and I have a pocket feature, and in this the system relieves automatically the geometry of my part. I have all the geometry of my part, and I can erase this hole. I have to make later with a spiraling cycle. Okay, milling of this with a pocketing cycle, and I set default to all parameter, and I choose to rough this, and also a wall finish path in my strategy. I choose the same tool. Okay, as usual, I have the preview of the tool, and I use the stock automation also. And for the strategy, I choose a concentric in. Total depth equal 35, and the depth, the incremental depth equal to the contouring operation. In the rough, I have parameter. Okay, okay, and I change the radial engagement. I change the step over for the radial engagement, 1.2, for example. Stock allowance 0.2 for a finish operation, and parameter for finish operation automatically in the same cycle, 0.04 and 0.04. Okay, and I want to make a finish pass at each Z level of the roughing. I validate. Okay, and I have my cycle. You can see the shape of the movement. You can see here a sharp corner in the movement of the tool for the first movement of roughing, but now directly on the simulation. Okay, I have the same tool, but you can see different color for a better visualization of your work. Okay, I can increase my feed rate. Okay, and the second depth. Is a little bit long, this operation. Okay, finish pass, and so on. The last operation, I want to finish, I want to machine this all with a spiral milling, spiral cycle, and is very simple. I have only to define my tool, for example, the same tool, parameter 7 and 0.07. And simply I have to decide the depth, of course, 20 millimeter, for example, and the incremental depth or the angle for the spiral, 0.5 incremental, and go. And I have the spiraling cycle. And now I can simulate the whole process. Okay. The movement between the tool change and the workpiece is automatically calculated to avoid collision and to have the better tool path related to the movement from tool change and to tool change. I accelerate my simulation. And at the end, we can see the elapsed time of my process. Okay, let me accelerate it a bit. Okay, now the spiraling cycle. Okay, it's done. And you can see the elapsed time at the end of all operation is 5 minutes and 53 seconds. Okay, now we have to optimize this cycle time with dynamic milling. Dynamic milling in ESPRIT is named ProfitMIliing. ProfitMIliing is a patented cycle of DP technology. For do this, I can erase my circular contouring, and I want to modify my rough operation. Okay, I simply change the tool with a TCDE tool, and I change the strategy, not concentric in, but I choose the profit milling. Okay, the system automatically manages the parameter for profit milling. I have just to decide the incremental depth. I choose all the cutting length, 35. In the rough, I have another important parameter. I have to change parameter 300 and 0.1 per tooth. Okay. I have a maximum feed rate, and I have another important parameter. This is the engagement angle. I can change the radial engagement, or I can change the engagement angle. For example, 37, and automatically the engagement change. Okay. I have the same stock allowance, and I change the parameters also for the finish pass to this. For example, with the same feed per tooth. Okay, I validate. And now you can see the profit milling cycle. What is profit milling? It's a roughing strategy. It's an high-speed material removal cycle. And with this cycle, you have a smooth tool path, and you can have a significantly deeper, faster, and more efficient cut. And we have the possibility to reduce the wear on the tool and on the machine. How it works? How it's possible to reduce the wear? Because the profit milling cycle reduce the head on the tool. Because let's see the simulation. Okay, this is the simulation. Little bit. Okay. Okay. When the tool starts to work, it reaches the temperature of processing, and the temperature remains constant for all the process. This is because the wear increased. Okay. The tool life increased, sorry. Okay. Okay. Now I have to change also the spiral. Oh no, sorry, another important thing on the profit milling. If you look at the tool path, you can see this movement in Z. This movement is 0.1 millimeter. Is a small Z directional lift to prevent the tool from dragging on the machine surface, and is done automatically by the profit cycle. Okay, now we change also the parameter for the spiral. Okay, validate and simulate, and have a look on the elapsed time. Now we can see a reduction of the cycle time due to the profit milling cycle. Okay. We have the other cycle. Okay. 2 minutes and 23 seconds. Okay, excellent. Another important thing of the profit milling cycle is the continuous variation of the feed to maintain constant the chip volume in the unit of time. If you look at the G code, for example, for this machine, this is the G code, you can see the variation of the feed in continuously variation for you have a constant chip load and the constant load on the tool. This is a typical profit milling cycle. Okay, this is done. Now I want to show you the behavior of the profit milling in the pocket. Also for this workpiece, I have already mounted my fixture and my stock on the machine table. Okay, and I want to program this pocket graphic. I choose all my workpiece and go to feature pocket, and I have the geometry of the pocket and directly milling, pocketing, and with 2 or 3 simple parameters, I can manage my cycle. I choose my tool, 20 millimeters TCDE. You have the preview as usual. And I use automation, of course. And the strategy, I choose profit milling. The total depth is automatically from geometry, and I want incremental depth of this 3 times the diameter of the tool. Okay, I have a parameter for total full engage, but I want to manage the profit milling parameter, for example, 350 meter, okay, and 0.25, 0.25, and this is the maximum. And a larger engagement angle, for example, 45 degrees. It's a radial engagement of at 3 millimeter. And I want an helical for my entry movement. And just I have to decide the radius, the maximum radius, and the helical angle, for example, 2 degrees. Okay, and the system automatically decide where to make the helical entry. Okay, go calculate, and this is the cycle, the profit milling cycle, and I want to show you the behavior of profit milling in the corner. Very important for us is the corner picking. Remember, this corner have a radius is that is minor than the radius of the tool. But in the corner, the behavior of the cycle is this is a smooth, very smooth tool path to prevent chatter, for example, the chatter of the tool to increase the tool life, for example. Okay, this parameter, this behavior, this trochoidal movement is automatically, yes, but it's possible also to manage directly in ESPRIT with this parameter. I can manage the minimum corner radius. For example, if I want to 0, if I put to 0, I recalculate, and the last pass is 90 degrees on the corner. It's not good for the tool, but if it's possible to manage. The cycle is totally automatically, but I can manage all the parameters. Another example, if you look at the simulation, for example, now I have a particular behavior. It's from top to bottom. The tool work recognize the geometry from the top and work to the bottom. It's not bad, but it's very long and produce a very long cycle time. Let me accelerate the process. Okay. Now level 1 completed. Now level 2, level 3, and so on. And this is more expensive in terms of cycle time. In ESPRIT, we can automatically change this behavior from top to bottom in bottom up with only one click. The system recalculate and I can simulate. Okay. We see that it works at the maximum depth. Okay. And after which it go back to cleaning only the area where there is still residual material. Let me accelerate a little bit. Okay. And this drastically reduces the cycle time. And you can get it just with a click. The previous cycle time was 25 minutes. This is, I don't remember exactly. It's half time the first, I think. Yes, exactly. The first cycle time was 25. This is 12 minutes. Okay, this is the ProfitMIliing cycle in ESPRIT. Okay, I have done, but I'm available if you have any questions. I'm here.
Yeah, thank you, Andrea. Yes, as I told to all of you before, if you have any question, there is the question area or just the chat where you can post it. And I think really that what we see this morning is a new way of cutting and roughing, thanks to the tool from Kennametal and thanks to the ProfitMIliing cycle. So the combination is really impressive. I think it's really important, also based on the Industry 4.0, that it's forcing us to, let me say, to be more closer and to be closer. It means that hardware, like a machine tool or tools and software, needs to work together. So if we want to have a better process on our manufacturing, definitely we need to work together. So our guest partner this morning, Kennametal, really helping us to use in a better way the tools to our customer, and on our side with the ProfitMIliing cycle, we are helping them to use their tool in the correct way. So the combination is really something that is helpful to all our customers. I don't see any question inside the chat. So if it's okay for you, I want to thank Gianfranco for the time spent with us and for all the technical days that you shared with us.
It's been a pleasure.
And to Andrea for the nice presentation.
Thank you too.
Thank you, everybody. Hope to see you soon in a future webinar. Have a great day.
Have a good day.
Thank you all. Bye-bye.